understand biliary secretion, and it's a really simple topic. So let's understand it really fast. So biliary secretion, I mean secretion. So biliary secretion happens from the liver, and so bile synthesis of bile liver makes synthesis of bile, which is 90% water. So it's really aqueous. So anything which is like hydrophobic will not bind to bile. That's very important. And anything that is hydrophilic, it can bind to bile. So gallbladder is the storage site of concentration of the bile, and usually it concentrates this bile, and the aqueous percentage goes from 97 to 87. It's like it reduces like 10% of water from the bile. So that's one concept. So that's why you need gallbladder. So if we remove this gallbladder, if we resect the gallbladder, we will not be able to have good quality of concentrated bile in our small intestine. So that's the bile. So function of bile, we have digestion and absorption of lipids. So that's one of the main function. Excretion of bile pigments and cholesterol. Okay, so bile pigments and cholesterol, really important. Okay, so constituents of bile. What is bile really made up of? So bile is made up of it's made in liver, right? And we have something called as primary bile acid, that is cholic acid and chenodeoxycholic acid, right? We have two of these important primary acids. Now, with the help of intestinal flora, that is bacteria, only bacteria have these enzymes, the intestinal bacteria. That's why they can do the job. They can convert primary bile acid into secondary bile acid. That's very important. Now, this primary bile acid is present in the liver, and this secondary bile acid is present in the intestine. Now, why the hell do we want to convert primary into secondary? Is it just because of intestine? Let's try to understand it. So let's go to the story. So bile is made up of three things: bile acids, cholesterol, and phospholipids. What are these bile acids? Cholic acid, chenodeoxycholic acid. So we know bile acid. Cholesterol, we know cholesterol. Bile pigments, we know bile pigments. And bile pigment is bilirubin. And phospholipid, we know phospholipid is used in a lot of things. By the way, phospholipids are negatively charged. That's very important. So bile acid, cholesterol, phospholipid, bile, bilirubin, water plus electrolytes. Important stuff. What is electrolyte? Electrolyte is HCO3 here. So what happened here is that liver converts this cholesterol into cholic acid and chenodeoxycholic acid, right? Here, these acids, right? They come from cholesterol, right? So cholesterol make these two things. So now we have these two things, cholic acid and chenodeoxycholic acid. Now this is primary cholic acid. Now these acids are too hydrophobic, mean they are really oily, right? They cannot stay in the aqueous position, right? So we want to change that. So what happened here is that these acids are too hydrophobic because they come from cholesterol. Of course, cholesterol is a fat molecule. So what happened here is that the conjugation happened. Now, the conjugation, it means, what is conjugation? The process by which you convert a product from hydrophobic into hydrophilic. That's basically conjugation. So conjugation happened. So these hydrophobic acid, now they became hydrophilic. And now we can, safely put them in this aqueous mixture of this thing called bile, which is usually 97% aqueous. So we want these acids to be hydrophilic, aqueous living. They can be binded with water. So that's why conjugation is done. So from bile acid, right, and that's how they become water family. From hydrophobic they become hydrophilic, and now they are in this bile. So bile salts, right? Let's talk about bile salts. What is bile salts? So that is basically the conjugation, right? So we get cholic acid, right? We have cholic acid and chenodeoxycholic acid that's coming from cholesterol, right? And then we have this conjugation happening. Then these acids, they become hydrophilic, right? That's the idea right here. And it's done via intestinal flora. These bacteria, they do it. And then we have these secondary bile acids, right? And they are in the intestine. And these are deoxycholic acid and lithocholic acid, right? And right here, they come from this. For example, this chenodeoxycholic acid makes deoxycholic acid, and cholic acid makes lithocholic acid. So that's the thing here. Both of these acids are lipophilic. Okay, so now they get they're getting conjugation done in the liver, right? And with glycine, with taurines, plus some sodium, right? And then we have something called as bile salts. So salts is just sodium in it, right? And glycine and taurine are used for the conversion. So in the end, we have this product called bile salt that is called sodium glycocolate salts. Okay, so we have these bile salts. Now these are salts, and we use these salts to, okay, I'll tell you what bile does later on. So now this is the whole story of bile. Okay, that's how you convert primary into secondary, and this secondary is done via intestinal flora because of these bacteria. They have these great enzymes, and these secondary bile is very lipophilic, and these secondary lipophilic acids, with the help of sodium, we get bile salts, right? That's the concept here. Now these bile salts, they can be used as detergent. For what? For fat globules, for the digestion of fat. Okay, so that was constitution, that was the bile. Okay, enterohepatic circulation, amazing. So purpose is to minimize the energy consumption during bile synthesis. Bile in liver and gallbladder is right. Bile is made in liver, stored in gallbladder. So it is going to the terminal ileum, right, for the digestion of fats and shit. Not shit, but that's just fat. And it does it works, and it's recycled back inside the liver, and it saves like 95% of bile is recycled every time, right? And this recycling is done around 6 to 8 times per day. So only a small 5% is lost in our shit, in our poop, and that's how the cholesterol is removed from our body. So very less cholesterol is removed, right? Now imagine if we have to remove a lot of cholesterol. What we can do is that we can actually stop this circulation. We can reduce the number of circulation, and then we can remove a lot of cholesterol. So that's like the concept of cholesterol removal and the concept of enterohepatic circulation. Note that the bile that arrives from terminal ileum to the bile is done via portal vein, right? That's very important to remember. So that was bile secretion. Let's try to understand the factors that affect bile synthesis. Now, bile synthesis, right? Cool, very simple concept. Let's try to understand. So we have this thing called choloractic, right? And choloractic means it increases bile synthesis, and cholagogos. Okay, someone can, my pronunciation is so bad. So cholagogos. I think it's not cholagogos. So how we pronounce this is cholagag. So these cholagag and these choloractic, this is just the things, the chemicals that can positively, just induce. Yeah, that's a good word to use here. These are this, for example, cholagogs is just a medical term, and it is done for the things that can increase the contraction of gallbladder. And we know gallbladder is the site of storage of this bile, where 97 gets converted into 87% of bile concentration, where basically gallbladder is actively removing H2O, water, from the bile, right? Let's talk about choloractics, right? These choloractics are the chemicals that can increase the bile synthesis. So by definition, choloractics are the substances or chemicals or drugs, whatever you want to call them, that increase the secretion of bile by the liver cells, by the hepatocytes, right? They simulate bile production. Now, it's just not in the flow. They actively increase the function of bile. They actively increase the, not the function, the flow of bile, the synthesis of bile, right? Before going into this choloractics, let's understand what this bile does. And again, so bile salts, right? We got bile salts by conjugation, right? And by converting primary bile acids into secondary bile acids, because secondary bile acids are more lipophilic. Sorry, not lipophilic, hydrophilic. Okay, so bile acids, they emulsify fat, right? They from big to small droplets of fat, we call it emulsification. Plus, Bile has this thing called, where is this thing called bilirubin. Now this bilirubin is an excretion of hemoglobin. It's a breakdown part of hemoglobin, right? And then we have cholesterol and phospholipids, right? They maintain the solubility balance of bile in aqueous position in water basically. And then we have water and electrolytes, right? So okay, so we understand that. So the main action of this cholerectics is that they act mainly on hepatocytes, right? And they stimulate the production of bile. Now this can happen via direct, right, or indirect, that is humoral, or it can happen in a reflux way. So direct is just that these drugs, they increase the activity of hepatocyte enzymes, right? And these bile salts, they themselves act as a feedback stimulation, right? They themselves can go and increase the bile secretion. Okay, so that's important. What other things? Humoral pathway, right? The indirect pathway of cholerectics things, right? Cholerectic substances. So some hormones like secretin, right? Here is the secretin. It works via humoral. Oh, okay, how? So these they increase the bile flow, and they increase the bicarbonate flow from hepatocytes and from these cholangiocytes, right? From pancreas. So how secretin does it? Secretin, right? It gets released in the presence of acid chyme in the duodenum from the S cells, right? So S cells, they make secretin. Secretin acts on these cholangiocytes. These are the bile duct epithelial cells, right? And they work on CFTR channels. We know CFTR channel produces chloride, and then chloride is exchanged, right, with this. Okay, let's go back here. So this was CFTR channel right there, and this CFTR channel is cystic fibrosis transmembrane conductance regulator, and this CFTR channel is positively, okay, wait, let me write it again, positively upregulated by secretin. So we have more chloride, then this gets exchanged, then we have more bicarb, right? So we have this cholangiocytes, CFTR channel, chloride leads to this exchanger mode, then we have bicarb rich bile flow. Okay, cool shit. What about bile salts? How they themselves can positively affect? Well, they act on something called as FXR in liver. Okay, and what happened here is this FXR, right, and it increases the bile salt export pump, right? These are the exporting pumps, right? And they work in a positive feedback loop, right? Bile acid dependent bile flow system. Okay, so the concept here is this was in short. Let me just explain you a little better. So concept of bile flow is that bile flow is the movement of this bile from hepatocytes to this bile ducts. Okay, let me just write it because it's better to just write and you will remember. So what happened here is this bile, right? It goes to this thing called canaliculi. Okay, then it goes to ducts, right? Then it goes to gallbladder, right? Gallbladder, right? Now from gallbladder we have this duodenum, right? So this is, right, this is the movement of bile, right? Normal movement of bile. Now the formation of bile is done in the hepatocytes, and the excretion is through caniculi, right? Okay, caniculi and the ducts, right? So major component, right, here is that first is hepatocytic activities, right, because hepatocytes are making the bile. Second is bile salts, right, because they are the components of bile. Third is the caniculi transporters. They what are these, by the way? What are they? I should tell you. So they are actually ATP dependent. They are ATP dependent transporters. Okay, now what are they transporting? Let's understand. They are ATP dependent transporters, right? And they push bile, right? They push the bile. They push bile. They push bile into caniculi, right? So we have these ATP dependent transporters, right? We call that canicular transporters, right? They push this thing into this, this caniculi, right? And this leads to this osmotic gradient, and water. This is why it's so aqueous. No. If someone asks you why this bile juice, which is supposed to be so lactic, right? So it's amazing. It has so many lipase activities, right? How the hell it's so aqueous in nature, right? Because because of this thing, it's called osmotic gradient, right? Now because of these transporters, these transporters called caniculi transporters, they not produce, they actively push bile acids, they push bilirubin, they push phospholipids into this caniculi, and then due to this osmotic gradient, water is flown into the bile flow, and this is how the bile flow increases. So that's the concept, right? Right there, that's the concept. Now, the correct term for bile caniculi, right? What is this bile caniculi? These are just these tiny little bit tubular channels, right? These are these channels between two adjacent hepatocytes. That's it. Okay, so that's caniculi for you, and they are amazing, right? They imagine like just two liver cells, two hepatocytes. They are just pressed against each other, and their membrane are like against this each other, right? And they make this slit, right? And this is like a tight junction. So that slit is called this bile caniculi. It's like a window. That's it. And bile flows from them. And because of the concentration gradient, water flows, right? That's why bile is so watery. Okay. Other thing is that we have these ducts, right? Ductal secretion, right? And what here happen is that we have this story, right? Wait, let me take my marker. Yes. So what we have this story called secretin. Due to secretin leads to bicarb being released in these ducts, right? So now the bile has, bile salts, phospholipids, bilirubin, and some water. Plus, because of the duct has a lot of bicarbonate, and now ducts lead to bicarb being inside this whole mixture, and then we call this whole thing a bicarb rich bile. Okay, so this contributes to this watery bile again, right? Okay, so that was this thing. We have this. I told you about this vagal stimulation, didn't I? Okay, I didn't tell. So this vagal stimulation is that this is a cephalic stage, right? We see food, we are hungry. What happened here is that this cephalic stage, it has two action. First is acetylcholine acts on gallbladder, smooth muscle. Now again contraction happens, cool thing, acts on hepatocytes, and then more metabolism. So cephalic stage leads to this contraction of gallbladder and the hepatocytes being more active. So vagus nerve, right? And we know that vagus nerve, these CCK, the secretin, and these hormones, right? They can adjust the function of bile. But cephalic stage, when you're gonna eat that baklava, right? So that's how the vagus stimulation connects with the cholinergic substance, right? Okay, cholagogues. Okay, they increase the contraction of gallbladder. So in other words, we can say acetylcholine is one of the cholagogues, right? Okay, so what happened here is that this thing called CCK, right? We know CCK, right? CCK is present in blood. Now what happened here is that the fatty acids, right? Fatty acids, they go to eye cells in the duodenum. The presence of fatty acids is seen by eye cells. Eye cells like, oh, we have so much fat, we need to do something. What happens is that this eye cells make CCK. Now this CCK is present in the blood now. Now this CCK goes to CCKA. Now we already know there are two types of CCK receptors, CCKB and CCKA. CCKA can positively increase acid production and can negatively decrease the acid production. And CCKA can inhibit CCKB. We already know about that. Now this CCK is getting activated by CCK. And then what happens that we already know this, that CCK, something called as cholecystokinin pancreasin, CCKPZ, can increase the construction of gallbladder, and we know that it's like increase the pancreatic enzymes in the secretion, right? So what happened here? What's happening? CCK goes CCKA on the smooth muscle gallbladder, okay, and via calcium and IP3 we have more bile inside the blood now. So in the blood simultaneously CCK relaxes sphincter of Oddi, right? And we know this sphincter of Oddi is needed for this bile flows from the contracted gallbladder. So the contraction, okay, so we know now we know that CCK PZ can lead to contraction of this gallbladder contraction, and CCK A, right, can lead to this relaxation of this sphincter of Oddi, so that the bile can get secreted from this contracted gallbladder. So CCKA important, CCKB very important for the acid regulation, and CCKPZ for the contraction. And this cephalic stage, acetylcholine acts on gallbladder smooth cell, and more contraction is happening. So it's like a whole, circuit. A lot of things is happening together, and it's so beautifully done. And it just makes me so happy. It's like reading about this. So that's like the concept about it, right? So let's talk about a little bit about intestinal secretions. So intestinal secretion are aka succus entericus. Nice name, by the way. Succus means juice, entericus means intestine. So juicy intestine. The site here, this is called crypt of Leberkun. Leberkun. I hope it was not that. Leberkunt. Okay, so crypt of Leberkun. Now, gland is located between two villi. This crypt, right? This is a crypt. This is a crypt, and this is located in. So let me just make it. This is one villi. This is second villi, and this is my crypt of Leberkun. Okay, Leberkun. So in this Leberkun, we have three type of cells: goblet, epithelial, and panneth. Now, goblet, as you can remember, goblet produces mucus, and it's done for the acid, neutralization. Because we need some mucus, we need watery mucus, so that our so that our intestine are healthy. Epithelial cells, right here, epithelial cells, they are the source of succus entericus, right? They make something called as alkaline juice, right? And the most important here is that panneth cell. Now, these are present on the base. They have high concentration of zinc. Zinc is the cofactors for many biochemical processes. That's why they have high concentration of zinc, and they produce something called as defensins and lysosomes. Now, these defensins and lysosomes are amazing for antibacterial bodies. Note that defensins and lysosome are also produced by where, okay, I read somewhere, okay, I don't remember right now. Okay, so these defensins and lysosomes are very important for these antibacterial activities. Okay, so here was the whole thing. Note that the stem cells are also produced on the basement membrane of these crypt Lemberkhan, and neck cells of gastric glands have stem cells. That's the most big difference between these cells. Okay, now other concept here. Now, as you can see, there is like mentioning of these two things. Let me write. Maximum potassium secretion. Now, why potassium is secreted in the saliva? So that it can balance, because naturally sodium is reabsorbed from the ductal cells of the saliva, right? To maintain the ionic balance, the acinar cells of saliva, right? The acinar cells of glands, they produce potassium inside the saliva so that we can balance it out. Okay, and maximum concentration of colonic secretion, right? So why it's written? Why even like this line called maximum potassium secretion in the saliva and maximum potassium concentration colonic secretion sounds very similar, right? But it refers to completely two different physiological ideas, right? So this is, by the way, this is rate. The idea is here rate, how much, and this is just density, like how much, right? How much per ml, that's the density. So meaning here is that in saliva, the meaning is that when we say that potassium secretion is happening, we mean that epithelial cells are actively like moving potassium from the blood, from the plasma into the lumen of the acinar cells. So saliva, gastric juice, these are like really high in potassium. And when I say that maximum K concentration is present at the colonic secretion, I mean that salivary glands have very active K secreting mechanism, right? When we produce saliva, we have these isotonic means less concentration, less the gradient. Water moves from plasma inside the saliva. So that's why it's isotonic, not isotonic, hypotonic. Okay, so saliva moves through ducts, right? And it has more potassium and it has less sodium, and it's hypotonic, right? So we understand this. So when I say this maximum potassium concentration of colonic secretion, I mean that in colon, especially on the distal colon, right, the last part, the distal part, the cell actively release a lot of potassium into the lumen under the influence of something called as aldosterone, right? So aldosterone releases a lot of potassium inside the lumen of this distal colon. So the volume of this colonic secretion is very small, okay, but the concentration is very high. Why? So that the amount, right, secreted by this, so the amount of potassium secreted may be small, but the concentration is really high. And that's why in severe diarrhea or colitis, the patient loses a lot of potassium. That's why, because loss of fluid lead to aldosterone, and aldosterone leads to a lot of potassium being secreted inside this distal colonic. So let me write this. This is a good concept. I don't know why I didn't write it. So concept here is that in diarrhea, right, loss of fluid, right, and it leads to aldosterone, and then this aldosterone goes and it just secretes potassiums inside the lumen, right? And that's why we have this hypokalemia, massive hypokalemia. So that's the concept, little bit. Okay, so the last line written here is it's measured in milli equal of liters, right? Okay, so that's it. This is the unit. It's measured in milli equal. So that's it, I think. So that's the whole concept of this intestinal secretion. That's the concept of biliary secretion, right? So I hope we understand that it's really simple, and it's really nothing hard, honestly. So have a nice day. Bye bye.